All right, welcome everyone to today's seminar. Today we have another set of early career speakers, Hugh Sun and Luisa Capannolo. Our first speaker today will be Hugh, and he will be discussing reconstructing ionospheric TEC and the VISTA algorithm and the VISTA dataset. So Hugh is a second-year PhD student of statistics at the University of Michigan in Ann Arbor. His interest lies in the spatiotemporal process and modeling and scientific-driven machine learning applications. He is currently collaborating with the Solstice Research Group at University of Michigan on both solar flare forecasting and total electron content forecasting. Hugh, if you would like to start.
Thank you, Kyle. Let me do screen share. Did you see the screen share? Everything working fine? Okay. Yep. Hello, everyone. My name is Hugh Sun from Department of Statistics, University of Michigan, Ann Arbor. I'm a second-year PhD student. So today's topic is about reconstructing ionosphere TEC. I'll talk about what TEC is very soon. And then talking about our newly devised algorithm of dealing with this reconstruction issue, which is called the VISTA algorithm. And finally, there is a dataset product that I also want to advertise a little bit, which is called the VISTA dataset. So there are several related papers related to this project, and also some database products that I wish that I can share somewhere, maybe for this slides or maybe a few websites that are related to this project. But I'll share this along the way in the chat box if needed throughout the presentation. So in this presentation, I'm going to very briefly talk about the scientific background behind. I think a lot of people actually present in this seminar here are actually more of an expert compared to my understanding for this domain. I'm from a statistics background, so this project is more like a data-driven project, and I definitely wish that I could hear more scientific insights in this if you are an expert or have some experience dealing with the TEC data before. And then I'll talk about the algorithm and database in succession. So first of all, it's about the data set. So the total electron content map is the ionosphere total electron content, which I'll refer to as TEC. It's defined as the total number of electrons in a pathway between the satellite radio transmitter and a ground-based receiver. So why is TEC so important is because it can affect the propagation of radio waves. It can also affect the positioning, navigation, timing service, the PNT service. So definitely we want to have a better understanding about the global distribution of this total electron content value around the globe. But what really makes this task a little bit difficult is that it really depends on the presence of a ground-based receiver to measure this particular quantity at any location on Earth. So the question is then, we don't really have a ground-based receiver everywhere around the Earth. We only have a selected amount of ground-based receivers on the main continents, but we have very small amount of ground-based receivers on the oceanic areas, leading to a huge missing value problems in the TEC database currently available to the community. So to give you a visualization about how the TEC data looks like, on the left-hand side, I'm showing a so-called Madrigal TEC map from the MIT Madrigal database, where you can see that there were actually a lot of white pixels, which are basically missing values. We don't really have ground-based receivers. We are not really observing any TEC values there. There is a significant amount of data that are actually missing in this data set, which is measuring up to 74% overall. In the middle column, we are actually applying a very simple smoothing algorithm to impute the local areas around all of the observed pixels to reduce the missing percentage. But even after you apply the so-called median filter technique, you can still end up with around half of the data missing, which is 50%. On the right-hand side is actually another database, which is called the IGS TEC database, which doesn't really contain missing values. First of all, thanks to a smaller amount of ground-based receivers that IGS is actually using. And secondly, they're actually applying additional smoothing algorithm to make sure that there are no missing values out there. So in this project, what we are dealing with is actually the data in the middle column. We are processing a little bit of the Madrigal TEC map, and we are trying to make sure that we are dealing with some database with half of the data available and half of the data missing. And what we really want to achieve is actually to impute or filling in reasonable values in these white pixels, especially in the oceanic areas where you can see that there are actually a contiguous region where we don't really have any observation at all, but we do have some neighboring informations. This is where the statistics methodology can jump in and help a little bit on this. Okay, so the total electron content map here, the research goals are twofold. Number one, we want to come up with a new algorithm for reconstructing the Madrigal TC map. We want to fill in a blank, fill in the missing values. Secondly, we want to construct a new TC database based on the devised algorithm and definitely also the Madrigal TC map, which is our source data. So let's talk about this one by one. First of all, is about the algorithm. So the algorithm involves some statistics sophistication in here that I'll just very briefly talk about the mathematical concepts behind. So what this algorithm is able to achieve is actually, it is trying to deal simultaneously of multiple TEC maps in a temporal sequence. We're actually dealing not only with a single TC map, we're actually dealing with a series of TC maps, maybe 200 and 300 at the same time, and trying to impute all of them in one algorithm run. And then we formulate everything just simply as a matrix factorization algorithm. So if you're not really familiar with the term of matrix factorization, it's fine. I'm going to show you exactly what I mean by this. But overall, if you want to refer to the statistical methodology behind this, it is actually the matrix factorization, matrix completion algorithm. And because we don't really have any understanding or knowledge about what those missing values are, so maybe it is a good choice for us to give kind of an initial guess about what those missing values are based on another different algorithm, which we call auxiliary data in our conceptual framework. So we are going to apply a so-called spherical harmonics algorithm first to impute a TC map, just give us a kind of an initial guess, a warm start, and tell us some initial knowledge or initial understanding about what is the possible TC values in those missing region are. And then we will start from there and then do the matrix factorization to even further update or improve the performance of our imputation. So these are just several features about what this algorithm is able to achieve. It is going to output a low-ranked imputation in terms of matrix rank. And it is going to guarantee temporal smoothness of the imputed TC map. So between any two adjacent frames in the Madrigal TC map, the Madrigal TC map has a 5-minute temporal resolution. We want to make sure that after every 5 minutes, the TC map doesn't really change much in terms of the imputed result. And finally, we coined a new term called VISTA because our algorithm is basically, its full name is called video imputation with soft impute, which is a statistics methodology. Temporal smoothing, because we want to guarantee the temporal smoothness, and auxiliary data, because we also inject a warm start to the algorithm to give us some initial guess. So it is called VISTA. So the whole algorithm is formulated as an optimization problem. It is a minimization problem with the following objective function. It has some notations in here, but generally it is just 4 different terms that I just line them up in 4 separate rows. So the first term is actually the so-called reconstruction loss, where the xt right here, they are the source data that contains missing values. You can think about them as any data, but here it is actually the TC maps contains of missing values. And all of the xt's, they contain observed values indexed by this omega t. So we only observe TC values at selected locations. Around 53% are observed. And then the imputed values, they're actually denoted by a matrix factorization form, where every single TC map is going to be a matrix product of 2 terms, AT and BT. Both of them are unknown and has to be estimated based on our algorithm. But eventually, the imputation is going to be AT multiplies BT transpose. This is going to be the imputed result that doesn't really contain any missing values. Now, the reconstruction loss, which is basically the first line here, just simply calculate the residuals of your data against your imputed result, but only restricted on those points where we have observed values, because only at these locations can we evaluate the residuals. And we're trying to calculate, how well does the imputed matrix, the imputed TC map do on reconstructing the observed pixels at all the observed locations. And the second row, third row, and fourth row, there are basically three regularization terms. So here, what I'm showing, the second row is actually shrinking the two matrix vectors toward 0. We still want to make sure that we are conservative enough so that, generally speaking, we want to make sure that the imputed value is closer to 0, because a lot of the pixels are actually background pixels with near 0 TC units, TC intensity. And the third row here is simply trying to calculate the difference of the imputed result from two adjacent maps. One of them is at time t, the other is t-1. We want to minimize their difference to guarantee temporal smoothness. And eventually, we also have the auxiliary data, which is yt. Now, the yt are based on spherical harmonic splitting, which I'm going to visualize very soon. But we just want to make sure that the imputed result, AT-BT transpose, is also very close to the auxiliary data, which is the initial guess, based on a totally different algorithm that is fitted independently. So this is generally the conceptual framework or the mathematical formulation behind the algorithm. So let me give you some visualization to see what the ended product looks like. So here's a data pipeline, but I think I can skip this. Just directly go into some examples. So here you can only you can simply focus on the top row, panel ABC. So in the panel A, where we're showing the original Madrigal TC map, which is basically the matrix that we want to have some imputation upon. And the second panel, which is panel B, is actually the spherical harmonics fitted result, which is the so-called auxiliary data in our framework. So it is pretty smooth. It does captures these the structures in the original TC map, but it also has a lot of closed loop structure, typically because of the basis function evolved in the spherical harmonics algorithm. So generally speaking, it is a little bit over smooth, but it does give us some non-trivial initial guess, especially in the areas where we do not really have any neighboring information, like the oceanic areas in here, where the spherical harmonics is able to provide some initial guesses. And what the VISTA algorithm is able to output is actually in panel C right here, which is still preserving the original structure in the TC map, in the original TC map, also some structure from the auxiliary data, and eventually kind of come up with a new version, which is not exactly over smooth. It has some low rank structure if you calculate the matrix rank. And it does have some non-trivial imputation in the oceanic areas. So if you want to ask whether we validate whether this algorithm works or not, in the algorithm paper that we have already published in a stats journal, we evaluate this algorithm on a validation set, which it works actually better than using the spherical harmonics only. And also, we compared this methodology against a lot of other tensor completion algorithms, and it's also going out to be one of the best options to use. So this is some visualizations about how the algorithm works. And we want to dispatch the algorithm to a large scale and generate a so-called database out of this by generating this so-called VISTA database. So what this database is all about is actually the following. The workflow is pretty simple. We want to find for every single day of Madrigal TC map from the year starting from 2005 all the way to 2020. So there's a 16-year period where we have Madrigal TC data for every single day throughout the 16 years of time span. Every single day is going to be a MATLAB kind of array that consists of a lot of missing values. We want to put this into our fine-tuned algorithm because we have a lot of tuning parameters involved in the algorithm, and finally come up with some completed TC map, which doesn't really contain any missing values for the 16-year period. So eventually, the database is actually a TC database that does not really contain missing values for the year starting from 2005 all the way to 2020. It actually consists of 3 critical steps to generate this database. First of all, we have to handle some data outlier issues in the original Madrigal TC map, because the Madrigal TC map itself actually contains some outliers, possibly due to the malfunctioning ground-based receivers or maybe some other reasons. So we first need to remove these outliers. And then we have the same TC data, but without the outliers. And then we fine-tune our algorithm to generate the imputed TC data of the day. And finally, we do some additional post-processing to get the completed TC map. So there are 3 critical steps involved in here. Each step is actually carefully validated in our database paper, which is currently under revision. So there were 3 steps. The first step is actually to remove the outliers. There were 3 types of outliers that we actually identified in this database. 3 types of them. One of them is called the hardware outlier, which is due to the malfunctioning ground-based receivers. Probably the ground-based receiver is simply popping out ultra-high TC values unreasonably, and we want to identify them and remove them from our observations. Secondly, we also have the so-called distribution outliers. Potentially, there are some ultra-high TC values compared to the rest of the data in the same day that are just unreasonably high, and you can simply point them out in a TC histogram. If you draw a histogram for all the TC values available in the same day, they are clearly outliers. We also want to isolate these outliers out of the dataset. And finally, we also have some domain experts here at U of M that go through all the 16 years of data manually to finally remove some additional outliers that cannot be detected by the first and second type of outliers, which are so-called the patch outliers. So they basically do some visual diagnosis on the visualizations after we remove the first and second type of outlier and see whether there are additional outliers out there. And then we move on to additionally remove this third type of outlier and ended up with a new database, a new data set, which does not really contain outlier. And then starting from there, we'll fit our algorithm. So here I'm just showing one example starting in the year of 2011, November 28th, where we identify 3 types of outliers. So here, this is a 6-panel plot. On the top left panel, it is actually, we're showing the pixel by pixel average value, daily average value of the TC throughout the whole day for this particular day. Now, every single pixel in this particular map is actually showing the average TC value for this longitude and local time location. So there are some locations that are actually contains outliers that you possibly find it hard to observe by eyeballing, but there are actually some outliers in here. For example, at this particular location, we consistently observe very high TC value even during the night times, which is totally unreasonable. So we find them out using an automatic algorithm that we coded up. And there are some other types of outliers based on the TC distribution, as well as our domain expert visual diagnosis. So finally, we can locate where these outliers are. For example, the hardware outliers, we locate them exactly at this location. And then we try to remove them. There are some additional distribution and patch outliers, especially the patch outliers. We can observe some additional unreasonable TC values in the South Pole, as well as some other locations found by our experts. We remove all of these locations TC values throughout the whole day, and then move on to tune the parameters for our algorithm and generate the data set for this particular day. So let me just go directly to the final data set product, because I don't think I have enough time to talk about parameter tuning. But all of these are actually going to appear in our database paper, which we are going to submit by the end of this month again. So here's just an example of the current released version of the database, which is already online, and you can easily download from the U of M online repository. So this is one example of what the data set looks like. In panel A right here, this is the original data. This is the median filtered version of the data, which is also the source data, where we have going to apply our algorithm upon. And this is the VISTA fitted map, which is actually the available data in our database. And this is the spherical monics fitted map. Now, all of these channels are actually made available in our VISTA database, and all of these are actually fine-tuned. They're based on a carefully chosen set of parameters for our algorithm that are applied on the Madrigal TC map for this particular day. So just to summarize it up, because I think I already ran out of time. So we have proposed a new imputation algorithm called VISTA, which is combining some statistical methodology called matrix factorization, matrix completion, with additional modeling consideration like temporal smoothing and oscillator data in a unified framework to impute total electron content maps, which is the Madrigal TC map, with over 50% of the data missing. And then we also review global and large-scale TC structures and preserve the mesoscale structures, which has already been pointed out in our algorithm paper for this algorithm. And finally, we have a data set that covering 16 years with fine-tuned VISTA algorithm and outlier removal, all of the things, to help the community to facilitate their scientifically related research. That should be it. Yeah, thank you.
All right. Thank you, Hu, for a great talk. I have a couple questions. The first, can you share the website in the chat and any preprint link that you might have, if you do have one?
Let me just quickly share a new screen. Did you see the new shared screen? I'm just going to load the data, load the website. So this is where the database is, which is currently version 1.0. We're going to release an updated version, I think, by the end of this month. So, but the README file and all of the details are already here. I can put in the chat. Let me put in the chat. This is where the database is. And this is actually a website that contains all the information for our VISTA algorithm, which I can also put in the chat. So this website is more, it contains more information actually about the algorithm. If you want to see more about the details of the algorithm, you can actually fit our algorithm live by choosing different combinations of tuning parameters and just simply click on the update parameters. The algorithm is going to fit online. You can play around with this and then generate output from here compared to the original data set. So yeah, you can just play around with this. And we also release additional reports on the database, all the details in here. So if you want to learn more, just go to these two websites that I shared in the chat. Yeah.
Okay, excellent, thank you. My other question comes, what's the temporal cadence? I saw it on one of the pages that you brought up, but I'm not sure everyone caught it.
Okay, so this is actually the size of the data, which is 181 times 361 times 288, which are identical across the 16-year period. Now, 181 times 361, they are the spatial resolution, which is 1 degree of latitude times 1 degree of longitude. And 288 is actually the temporal cadence. So you have, throughout the 24 hours, you have 288 frames, which ended up with a 5-minute cadence. Yeah.
Excellent. And my last question is, you're doing a filling in of the data. Have you guys, you did mention that you did some validation. Did you do validation by removing points in the map that you had data for and then seeing how the algorithm performed, comparing to what data existed?
Good question. So we actually tested 4 different scenarios. Here, this is one example from our website. So the 4 scenarios that we are considering are actually the following. We randomly drop pixels for validation like this. So we have the original map, and then we randomly drop at random locations for validation purpose. But there are also some other cases where we actually throw out a complete patch, which are basically a cluster of missing locations in a kind of a square or rectangular shape of box, and we throw them away as a validation set and reapply our algorithm to see how it works. So we validate this on the IGS data because it has the original observations and try to check whether it works well. So actually here, this is one of the validation results that I want to show. We just simply throw away this 63 by 63 patch and reapply different versions of our algorithm. This is what the VISTA algorithm looks like. Compared to the severe harmonics, for example, it is actually numerically giving better result. If you want to check about the numerical numbers, is actually included already in our algorithm paper. But definitely, we have considered different types of validation, not just simply throwing away random locations, but also throwing away patches, which are actually, I think, a more common missingness pattern in the original Madrigal data.
Okay, excellent. Thank you for the great talk. If we have any other questions, we'll try to come back to them at the end if we finish with a few extra minutes.
Sure. Thank you.
All right. Yeah. So our next speaker is Luisa Capannolo. Luisa, if you want to share screen.
Yes.
All right. Luisa is a research scientist at Boston University and working with Professor Wen Li. She graduated with a PhD in astronomy from Boston University in 2020. Her work focuses on the precipitation of energetic electrons from the outer radiation belt into Earth's atmosphere due to EMIC waves and field line scattering. She finds precipitation events from a variety of low Earth orbiting satellites and CubeSats and looks for wave signatures in data from ground-based stations or magnetospheric satellites. She is currently using machine learning techniques to study and classify the drivers of precipitation. And today I'm happy to have her here talking with us about distinguishing the drivers and understanding the properties of relativistic electron precipitation in the night side. Luisa, if you would like to start.
Thank you. Thanks so much, Kyle. Thanks so much also for having me. And yes, so today I will show you our recent work in which we specifically focused on the night side precipitation of relativistic electrons. And so I will just show you a little bit what we found. Okay, starting from the top, as we know, the radiation environment can be affected quite significantly by plasma waves that occur in the magnetosphere, and these waves can both accelerate and precipitate electrons. And there's also another mechanism that's called the current sheet scattering, and I'll describe that a little later on, that is also occurring, and it can also cause precipitation of electrons. And so together, these two mechanisms can lead to some potential space weather effects. And in fact, the radiation environment, as it changes, it can potentially cause some damages to satellites or instrument degradations and so on. And on the other side, once the electrons are precipitating, these electrons cannot actually interact with the atmosphere. And there can also be some space weather effects on that side as well. So for example, the conductivity can be changed as precipitating electrons are interacting with the atmosphere. And so this can potentially alter the reliability of communication systems. And then also the actual chemistry of the atmosphere can be changed during precipitation. And this can ultimately lead to some ozone reduction. So this essentially kind of leads us to what are the main goals to kind of study precipitation. First off, we want to understand if waves or current sheet scattering are dominating in a specific MLT or L shell, and if one of the two is actually dominating across all of these sectors, or if there's instead some preferential region where, for example, waves are dominating. And on the other side, we also want to understand what is kind of the location, the spatial extent of the precipitation driven either by waves or by current sheet scattering. So relativistic electron precipitation that typically goes under the name of acronym of REP typically occurs between 16 to 3 MLT. And it has generally an occurrence peak pre-midnight. At least this was what was shown in this paper here. The sun is here to the top, and these dial plots are indicating essentially the occurrence of REP. And so as you can see, there's this peak of occurrence here, but the actual precipitation can extend kind of in this whole region, and some even on the day side. Typically, this kind of precipitation of relativistic electrons is also often associated with proton precipitation of energies between tens to hundreds of keV. And so this paper here is actually showing the simultaneous precipitation of protons and electrons. And so what they find is that there is this pre-midnight peak, but that there are also other kind of two peaks, one across midnight and the other one post midnight. So there seems to be kind of a slight difference between kind of the general REP and the more EMIC-driven REP, which I probably forgot to mention, but essentially whenever there's proton and electron precipitation, this is generally an indicator that EMIC waves are causing that precipitation. And as I mentioned before, there's also some current sheet scattering driven precipitation that can also occur, also relativistic energies. And so this paper here, they were showing, they looked at 38 days of LEO satellite data, and they kind of distinguished between wave-driven events in blue and the CSS-driven events in red. And so as you can see here across midnight, there's kind of like an overlap between these two mechanisms. And so this essentially kind of made us wonder if there's one specific mechanism across midnight that is dominating that precipitation. And so we kind of try to see if there's a certain L shell or MLT region where one of the two is dominating. And before I show you the actual results, I just want to show you a little bit kind of the typical precipitation pattern caused by plasma waves. So whenever there are plasma waves in the magnetosphere, these waves can potentially interact with the trapped electrons, and they can alter their pitch angle, and this is called pitch angle scattering. And because of that mechanism, these electrons can potentially fall into the upper atmosphere and interact there with the neutral atmosphere. And so essentially they're lost. And so this is another cartoon of that phenomenon. And if we have a POSE satellite or a LEO satellite that is able to observe electrons, once it crosses the region where that precipitation occurred, there's going to be kind of a pattern of the electron flux that is observed. So this one here is a plot that shows you POSE data, specifically the electron flux above 700 keV. So here we're talking about, again, kind of relativistic energies for electrons. And POSE is able to look at the precipitating electrons with the solid line, and also the trapped electrons with the dashed line. And so anytime that this solid line is approaching the dashed line, there's precipitation, because a good amount of precipitating population is actually approaching the trapped population. So in this region here, which is marked in gray, that's where essentially precipitation is occurring. And if this is typically associated with waves, just because it's rather isolated, and it actually occurs well within the outer radiation belt. And you can see, in fact, that there's enough population across both around the region of precipitation. And there's actually, if we look at lower energy electrons here, there's not really an energy dispersion. And this will come up later on when I show you the current sheet scattering profiles. So of course, there are many plasma waves in the magnetosphere, but since we're talking about relativistic energies, typically, whenever we think about a precipitation of electrons at relativistic energies, EMIC waves tend to be kind of the primary source of that precipitation. And these EMIC waves are kind of known to scatter or efficiently scatter electrons in this kind of afternoon dusk region. We've looked at several case studies, and we kind of tried to find a good association between EMIC waves and that precipitation observed. And we in fact found that for all of these case studies, the electron precipitation observed at LEO was actually associated with EMIC waves. And so this one here is just showing you a conjunction event where we have here in red the trajectory of RBSPA. And in this thicker line, RBSPA was observing EMIC waves. And EMIC waves, the spectrum of EMIC waves is shown here. And so these waves, as you can see, have a kind of rather low frequency between 0.1 to approximately 5 or so hertz. And they can also be distinguished in different ion bands. What we also saw is that in conjunction with RBSP, there were two POSE satellites crossing kind of approximately at 18, and they both observed relativistic electron precipitation. And so this one here is the observation from NOAA 15. And you can focus specifically on this red line, where again, the solid line is the precipitating electrons. And so this region here in gray is showing you that relativistic electrons were precipitating, and this profile was rather isolated and associated with EMIC waves. We've also done a quasi-linear modeling for this event and kind of proved that, or demonstrated that EMIC waves are likely going to drive this precipitation for this case. So moving on to show you the current sheet scattering instead, this mechanism occurs whenever magnetic field lines are stretched away from Earth, such that their curvature radius is going to be comparable to the gyro radius of the electrons. And so if that happens, typically the electrons are lost and kind of can again fall into the upper atmosphere. And with this mechanism, we can actually identify the so-called isotropic boundary, and at L shells above those, or higher latitudes than the isotropic boundary, there's essentially an isotropic distribution of electrons, which means that the loss cone is completely filled and the precipitation is occurring. So again, if I look at this cartoon and we have again a post-satellite crossing in this region, the profile of precipitation is going to look a bit different compared to the other case where waves are driving that precipitation. And so here, this is the data from POSE. Specifically, the red line again is associated with the relativistic electrons, and the other colors indicate lower energy electrons that POSE is actually able to observe. So in this case here, you can see that the red line is essentially approaching the dashed solid line, kind of at the edge of the outer radiation belt. And then if you look at lower energies, there's actually some energy dispersion. So essentially what you see is that these relativistic electrons are precipitating at lower L shells compared to lower energy electrons, which instead precipitate at higher L shell. And this is essentially given by the fact that high energy electrons and low energy electrons have different gyro radius. So the location where that precipitation is going to occur is going to change depending, it's going to change as a function of latitude. And so this is a typical kind of profile of what you can expect for current sheet scattering events. So there's this dispersion in energy. And this phenomenon has actually been studied quite widely, both theoretically and observationally for protons. And this one here is just a paper where they were looking at kind of different conditions of the geomagnetic activity and showing the isotropic boundary as a function of MLT. And so as you can see, there's kind of like this isotropic boundary is at lower latitudes, kind of around midnight, and it increases towards the flanks and up to the noon. And so this essentially kind of suggests us that the current sheet scattering is expected to be more pronounced in the night side, also because the magnetotail there is much more stretched compared to the flanks and of course the day side. So essentially, knowing all this, we can kind of leverage the fact that the spatial characteristic of the precipitation is so different depending on what is actually driving that precipitation. And so we can use this to study specifically the precipitation across midnight. And so we have an algorithm that is based on flux thresholds for POSE. And we found approximately 4,500 possible events. And then we visually classified them between two main categories, those driven by waves and those driven by CSS. And so here I'm going to show you how these events distribute. So here is the scatter plot L shell as a function of MLT. In blue, you have the wave events, and in gray, the CSS events. And so as you can see, the majority of the precipitation is occurring between 4 to 7 L shells, which is kind of reasonable because that's where the majority of the population of the radiation belts is located. And then here you can see the distributions as a function, or as histograms as a function of MLT and L shell with the same colors. And so essentially, kind of overall, what we see is that both waves and current sheet scattering are coexisting in this sector. And in fact, there's not really a clear region in L shell or MLT where one of the mechanisms is dominating over the other, which essentially tells us that waves are equally important as current sheet scattering that region. If anything, there's probably just a small difference here in L shell. So the waves can potentially drive precipitation at lower L shells, while the CSS might drive precipitation at slightly higher L shells. But this is not a very big difference. What we've done next is also kind of associate these events with the magnetotail stretching. And we can do this if we use GOES observations. So we look for pose-GOES conjunctions, and we're able to calculate the elevation angle, which is essentially this angle here that is given by the components of the magnetic field that GOES observes. And so the smaller is this angle, the more stretched the field line is. And so here is again another typical CSS-driven event. And here at the bottom, I'm showing the conjunction of GOES 13. And so at the bottom here are the components of the B field observed by GOES. And so you can see in red, the earthward component that is kind of increasing towards the UT of precipitation. And then instead the poleward component is decreasing. And so this is kind of marking a stretched field line. And so this results in a theta or elevation angle that kind of decreases towards the precipitation. And this is indicating that the magnetic field line is stretched there. So we did this calculation for all of the events, or at least all of the ones in conjunction with GOES. And these are the distributions. So on top, the wave-driven events, and at the bottom, the CSS-driven events. These distributions are in gray, while instead this distribution in orange is indicating kind of the monthly averaged distribution of elevation angles that GOES observes. So it kind of serves as a reference point for what are the typical angles that GOES observes in that region. And so as you can see, the distributions in gray, which are those actually associated with the precipitation events, are actually shifted at lower angles compared to these orange distributions. And this is essentially suggesting that the magnetotail is stretched for both drivers of precipitation. The CSS-driven events are peaked at a slightly smaller angle, so maybe there is a little bit more pronounced stretching for these events. We've also tried to look at specifically the association between EMIC waves and precipitation. And in order to do this, we used an EMIC wave proxy. So essentially, we looked for events where not only there's precipitation of relativistic electrons, but also proton precipitation observed by POSE, because this is a typical signature that EMIC waves are actually driving that precipitation. Together with that, we also use conjunctions between POSE and GOES, and POSE and RBSP. And for example, this case here, we see the precipitation here, but from the observations of POSE, proton precipitation, we can't really tell much because this is not really an isolated precipitation. So we look for a GOES 13 in conjunction, and that satellite was actually observing EMIC waves. And so doing this kind of analysis, we found that the majority of wave-driven events are actually associated with EMIC waves, but only 14% of the CSS-driven events were associated with EMIC waves. And so this essentially suggests that EMIC waves might be the primary wave source for the precipitation of these events. What we did was also kind of like look at the distribution of specifically EMIC-driven events. And we found that this is very similar to the general wave-driven event population. So EMIC waves are able to scatter pre-midnight electrons as well as post-midnight electrons. But what was actually interesting is that the extent, so the delta L of this precipitation tends to have an asymmetry with respect to midnight. So if we plot here the radial extent as a function of MLT, you can tell that there's this kind of like triangular distribution. So pre-midnight events seem to be a little wider compared to post-midnight events. And so this could either be due to the EMIC waves that are actually changing their properties, or the background, conditions to actually cause precipitation. This is still kind of currently unknown. And so this is just my summary. We essentially used the fact that the wave-driven and current sheet scattering-driven precipitation profiles are very different, so that we can actually, just from looking at precipitation patterns, understand what the driver of that precipitation is. And it seems that both waves and current scattering are driving precipitation across midnight. And these cases occur when the magnetotail is stretched. It also seems that EMIC waves are the primary wave source for the wave-driven events across midnight. And there's some asymmetrical properties of the radiation, of the radial extent of this precipitation. So this, of course, leaves many open questions. First off, we want to understand the overall distribution of these events at all MLTs, so not just at midnight, and also kind of understand which one of the driver, if it's waves or CSS, that is actually dominating the total relativistic electron precipitation. Ultimately, also understand what are the effects on the atmosphere, as well as figure out if there's like a preferential phase of storm or substorms where one or the two mechanism occurs. And that's just my final slide as a kind of a shout out of what we're doing now. We developed a machine learning code that essentially is able to classify these events without having us do it manually. Because for the study that I just showed you, we essentially looked at 4,500 events and kind of manually classified them. And so this can be avoided with our code here based on machine learning. And this will allow us to essentially get more statistical data sets so that we can actually look at the distribution at all L shells and specifically at all MLTs. That's all I have. Thank you.
Hi, thank you, Luisa, for a wonderful talk. I have a couple quick questions. You showed the distribution of the CSS and the wave-driven, and it seemed to peak at around an L of 6.
Yes.
You generally didn't see a peak in MLT, but that L of 6 is roughly where you see injections. Do you think a lot of this is possibly related to substorm injections and substorm activity?
I think so, because I think typically EMIC waves are associated with substorm injections, and CSS events, if you think about substorms, they're typically occurring when the magnetic field lines are stretched or are becoming more stretched, and then there's the substorm. So yes, I do think that there's some connection with that. It would be interesting to just look at kind of how these events are correlated with, say, the AL index or something. We would have to do that. Yeah.
Mm-hmm. Cool. So Allison also has a follow-up question. Did you see any high latitude or high amplitude chorus waves during any of your relativistic electron precipitation events?
Yeah, so if I had the RPSP observations in conjunction, I could check for those, and typically those were not, I have never seen chorus waves associated with those. For GOES, I didn't check, but so I don't exactly know, but yeah.
Okay.
If you have any ideas on how, because I do think that we do need conjunctions with, satellites so that we can actually look at chorus.
Yeah. So there is one database. I can email you about that for conjunctions later on. That might help.
Cool. Yeah, absolutely.
So those are all the questions we have today. Thank you, Luisa and Hugh, for 2 really great talks. Our next talk is going to be by Allison Janes next week, and she'll be continuing the kind of discussion that we have for the summer on precipitation, and she'll be talking about the dynamic loss of Earth's radiation belts from moss in the magnetosphere to particle precipitation in the atmosphere. And this will continue a number of talks regarding magnetospheric precipitation. So thank you again, Hugh and Luisa, and I hope everyone has a wonderful week. One follow-up point, Luisa. Allison is suggesting that the pose-based proxy might help for chorus waves. And I think that's the proxy based on electron precipitation as opposed to proton precipitation. Is that correct, Allison?
I can unmute. Yes. I mean, when of course knows this proxy very well, but I just wondered if you could maybe try to correlate, since you're using pose data, you could try to correlate, chorus proxy amplitude based on that.
Yeah, I can certainly try. I think that proxy, I believe it was based on lower energy electron precipitation.
Mm-hmm.
And anytime I go to lower energies on pose, and there's relativistic electron precipitation and proton precipitation, I don't know how much we can trust the data because of the contamination, but I can certainly check. Yeah.
Okay, and I can send you a paper of
absolutely
Josh Pettit, who's actually been cleaning the electron data from proton contamination.
Yeah. Sounds good. Yeah, I know of that paper. I'm
actually
talk to him tonight. So
okay, great.
Good.
Very good.
Thank you.
Okay.
Yeah. And Josh is actually one of our speakers in the summer. He'll be speaking on August 22nd.
Wonderful.
All right. Well, thank you, everyone. Have a wonderful week, and I hope everyone is enjoying the summer. Bye.
Thank you.
Thank you.